Okay. There was a woman whose name is Floydell, and they did an experiment with her where they gave her 12 t-shirts. 6 were worn by people with Parkinson's disease. 6 were worn by people without. And she was asked, just by sniffing the shirts, could she detect whether or not they had Parkinson's disease? How many do you think she got right?
9. 7.
Higher.
10.
Higher.
12.
11. So she was able to correctly identify 11 of the 12 shirts as either having Parkinson's or not. Okay, which is pretty high. Okay, it would be very, very difficult to get that lucky. Okay, that was a different activity that I sometimes do with classes, but I'm just going to tell you about that as we move on from there. So, I mean, obviously, so a university picked up on this and they thought, I wonder if we can make a machine that could actually, through smell, detect Parkinson's disease. So this university in China, right, they created what was called an e-nose, and their system attempts to detect the specific mix of compounds that produce the distinctive smell of Parkinson's patients. Okay, and then this is just a picture of how they go about doing it. And so they tested this e-nose once they finished it on 24 people, 12 with Parkinson's, 12 without. Okay. So in a world where the e-nose doesn't work at all, as in it's only as good as random guessing. Like let's say it didn't work at all and then it just had randomly guessed. How many would you expect it to get right?
12.
All 12? Oh, sorry. I'm sorry. I was thinking the half, right? Yeah. 12 or 50%. And then as a proportion down here, it'd be 0.5. Okay. Well, when they did their first set of tests, this e-nose correctly guessed 17 out of 24, which is quite good. Okay. In your opinion, is this convincing evidence that the e-nose is more effective than just randomly guessing? I mean, possibly, but convincing? No, maybe it was just really good luck. Okay. So yeah, we would say no. This result could have happened by chance. Okay. Well, we want to test it. Okay. So when we go about testing something like this, to determine if there's convincing evidence, we would run a simulation, several trials, okay, where we would have 24 patients, half Parkinson's, half without, and then just randomly guess and see what happens. And did it 30 times. And out of the 30 times, this is what the results look like. So one time, a little under 30%. Another time, a little over 30%. A fair amount of the time, 50%, which we would expect. Also a fair amount of the time, a little below and a little above 50%. So we can see what's happening here, some extreme results don't happen very often, but some results that are close to 50%, what we would expect, happen often. And recall that the eNodes did 17 out of 24, or 70.8% or 0.708. So, looking at this simulation and what happened, would a result of 70.8 be surprising? I mean, where is 0.078 here? It's over here. It's way over here. How many times out of 30 did it happen when we just did it randomly? Once. So really, that would be surprising, okay? Because it happened by chance only once out of 30 tries. So yes, because this result happened once. Out of 30 tries. That above distribution, when we did the simulation and we ran 30, or we did 30 trials, and then we graphed them, what does that shape look like? A normal curve. And it turns out, under certain conditions that we'll talk about next class, we'll talk about what's conditions you have to meet in order to do what we're about to do. Okay, we can model the sampling distribution for a proportion, because remember, this is a proportion we're finding, right? The proportion that had Parkinson's, or the proportion that didn't have Parkinson's. And then what are we doing again? We're creating a sampling distribution. We've got what happens in the real population. We take several samples, and out of those several samples, create a sampling distribution. Well, it follows a normal pattern, a normal curve. And so we can model, and this is the notation that I use, the sample proportion will take a normal distribution. The mean of this sample proportion distribution will equal whatever the population proportion is. The standard deviation of the distribution of sample proportions will equal the square root of the population proportion times 1 minus that proportion divided by the size of the sample. You will be given this. Okay? This will be part of a formula sheet. Because remember how we did normal distributions way back in Unit 2? We needed to know the mean and the standard deviation. This is how we calculate the mean and standard deviation for sample distributions of proportions. Okay? So in this situation, we're assuming that the population proportion is half, right? So 0.5. So this would be 0.5. This would be 0.5, as with this, and then our sample size was 24 when they did that. So we would be able to calculate this and this. So therefore, we would say, okay, in our sampling distribution, it follows a normal curve. the average or mean of all the sample proportions we take will be equal to the population proportion, which is 0.5. And the standard deviation of that sampling distribution of sample proportions will be the square root of 0.5 times 1 minus 0.5 divided by the sample size that was taken, which was 24. And if you do that calculation, you're going to get approximately 0.102. So these values represent the graph at the top of this page. Okay. So this follows a normal curve, normal distribution. And remember, to answer questions about a normal distribution, we need to know the mean of the sampling population, which we said was 0.5. And we need to know the standard deviation of the sample proportion, which is 0.102, which we calculated below. And once we've got those things, we can calculate using normal CDF on our graphing calculator. And that's how we would answer the last question. So using the values that we got and the fact that we know that it's normal that we're dealing with, what's the probability that the eNOS gets 70.8% of its guesses or more correct just by chance alone? So remember, when we do normal distributions, we have to accompany our calculations with a diagram, with a graph. So we found the mean was 0.5, 3 standard deviations above, 3 standard deviations below. There's our normal curve. We know our standard deviation is 0.102. So if I add 0.102, I get 0.602. If I do it again, I get 0.704. And if I do it again, I get 0.806. If I started my standard deviation and started my mean and subtract the standard deviation, I get 0.398. Subtract another 0.102, I get 0.296. And subtract the final one, and I get 0.194. Don't forget to label. Remember, this is not the population proportion. These are all the samples we did and the sample proportions we did. These were all the p-hats we got. Every time we took a sample and calculated the proportion, that's a p-hat. And to complete your diagram, we want to know 70.8, which is just slightly above this notch. So we want to know the area of this section. That's a completed diagram. And then using our calculator, graphing calculator, we do normal CDF. And then we are asked to punch that into our calculator. And along with 4 values, what's our lower boundary? 0.708. What's our upper boundary? Yeah, 10,000, 1,000. Either one would be fine. Let's do 10,000. The mean of this distribution is 0.5, and its standard deviation is 0.102. And when you do that on your graphing calculator, you get 0.021. or about 2.1%. Which means that's very low. The probability of getting 70.8% of the guesses correct by chance alone or higher is just 2%. Where's the line where we say, okay, it's unusual and where it's not unusual? For now, just use 5% as a guide. Anything below 5% would be considered unusual. Anything above 5%, we would say, yeah, it could happen by chance alone. Okay, that's our guideline right now. We'll get a little bit more precise with that in units 7 and 8. So we would say the probability (2.1%) is so low that the result from the eNOS was 70.8%. Would be considered unusual. Therefore, we have convincing evidence. The eNOS was more effective than random guess. So like I said, with questions like this, with proportions, we get a result that happens. We want to see if that result suggests that convincing evidence that something works or not convincing evidence that it works, okay? And this is how we go about doing it. We take the result of what actually happened, and then we replicate that by taking several different samples, running the simulation. From that, getting the mean of all the sample proportions we got, getting the standard deviation, and then calculating the probability. So you can see how all these things we were doing before to this point are now coming together to allow us to start making conclusions. Okay. And then the next step is going to be, I can use those formulas and I can say it's normal as long as certain conditions are met. So as part of this, we're going to add conditions that allows us to say this, this, and this. We need 3 conditions to happen, but we'll talk about that next.